Welcome to the lecture on Bleichenbacher Chosen Ciphertext Attack on RSA. The agenda for this lecture is first we will briefly go through the RSA summary. Basically, we will see how the RSA encryption and decryption work with a real example using Python. And then we will also discuss about the multiplicative property of RSA which the Bleichenbacher attack is using. Then we will focus on public key cryptography standard 1 version 1.5 padding format which is used for encrypting the RSA text, especially in the SSL TLS protocol. And then we will see a simple example of it using a openssl RSA utility followed by a Wireshark packet capture, and we will see Wireshark how it is decrypting the encrypted pre-master secret when you provide a private key file. And then we will go through the what is a oracle and what is the chosen cipher text attack and the core concept of Bleichenbacher attack on RSA, followed by a very simple demo. For this demo, what we are going to do is we will take a real capture for which we know the private key. From the capture, we will filter out the encrypted pre-master secret. We will use as the known ciphertext in the Bleichenbacher attack. Instead of doing a real attack on a TLS server, I have written a oracle in Python. I will use that oracle to decrypt that encrypted pre-master secret so that you can get the plain text pre-master secret. Okay, so with that, let's start the lecture. So RSA, as you all know, is a public key cryptography algorithm. So how does it work? In the beginning, the RSA uses two large prime numbers. The prime number is called P and Q. If you multiply these two prime numbers, you get another number called N. This N is called RSA modulus. Typically, the value of N nowadays is usually 2048 bits, what we call as 2K key, right? So when we say RSA 2K key, we are actually referring to the size of this modulus. Okay. Now you subtract 1 from the P, you subtract 1 from Q, you multiply these two, you get another value called Z. Okay. Now you choose two value E and D such that when you multiply these two guys, you will get 1 mod Z. Usually when you work with the modular arithmetic, instead of equal, we always use this symbol, right? This symbol actually refers to equivalent, not exactly equal, it means equivalent. So E star D is equivalent to 1 mod Z. Now the N and E together is called public key. So where you can find a N and E when you use SSL TLS, if you are using RSA certificate, right? Inside the RSA certificate, you will find the modulus value and the exponent. In the past, people were using a very simple value for E, such that E equal to 3. But later, mathematicians and cryptanalysts found that it is not safe, so people no longer are using E equal to 3. Instead, nowadays, most of the time we will see E equal to 65,537. Okay, the reason for choosing a very small exponent value is so that the encryption will be much more faster. The D value, on the other hand, is a really huge number, almost equivalent to the modulus value, almost equivalent. So because the D value is so huge, D value is called the private key. Because it's so huge, the decryption is going to take more time. Okay, so this is the very brief summary of what is RSA public key and what is RSA private key. Now, how do the actual encryption decryption works in RSA? Let's say you have a message M, right? The encryption decryption is very simple. All you have to do is take your message, raise it to the exponent E. Your E is nothing but the public key. Okay. Then use mod N. That is what you call a ciphertext. Decryption is again same logic. use your ciphertext, raise it to the power D. D is your private key, and then you reduce it to mod n, and you will get back your message M. So before we move on to the further topic, let's see a quick demo using Python. How does the whole thing work? Let us see a quick demo of how RSA encryption decryption work using Python. So here I am going to use Python 3. So let me import from crypto.public key, import the RSA module. Okay. So let me create a key pair, that is the private key and public key using this module. So k equal to RSA dot generate. I want to generate a 2048 bit key using RSA. So it will generate. So if you don't know what all the things you can do with this object, just use the Python help command. It will tell you what are the things you can do with this key value. Okay. So now let's see each of the things we learned in the theory. So what is the prime number P and Q used to generate the key? You can find it. K.P will provide you the prime number P. Look at this. Very large integer, right? Look at the Q. It is also a prime number, usually very large. So I told in the theory, if you multiply this P and Q, you should get the modulus n, right? So let's see. Let's first see what is the modulus k dot n. So this is your modulus. It's very large because we have used 2048 bit as the modulus length. Now, as per the theory, if you multiply k dot p and k dot q, you should get this modulus value, right? Let's see whether we are able to get it. So when you multiply, we should always perform a, okay, let's multiply this. Look at this. We got the modulus, right? Ending with 3001, right? So that confirms that if you multiply p and q, you get the modulus value n. Now the next thing I discuss is z is equal to k dot p minus, that is p minus 1 star q minus 1, right? If you multiply p minus 1 and q minus 1, you will get what is called a z value. This you will need to create a e and d value. So let's multiply this. So what is the value for z? It is also a big number. Now let's see what is the e value that RSA has generated for us. K dot e is the exponent, right? I told you nowadays no one is using e equal to 3 because that is no longer safe. So most of the certificate you will find actually e value as 65,537. This is a small number, whereas the private key is going to be a huge number. Let's look at how the private key looks like. K dot d. Look at this. Really almost the size of the private key is almost the size of the modulus, right? It's almost near the size of the modulus. So private key is going to be really huge. That means encryption will be faster, decryption will be slower. Okay. Now I also told if you multiply E and D under modulus Z, you should get 1 because both E and D are inverse to each other. They are multiplicative inverse to each other under mod Z. So let's try to multiply this guy K da E and D. When you multiply, you should always do a modulo Z. So let's see. In theory, we learned that if you multiply E and D under mod Z, you should get 1, right? Let's see. Yeah, we got the 1. So that means E and D are modular inverse to each other. So okay, we don't go further. So using a Python, we learned how RSA encryption and various value used in RSA, that is prime number P, Q, modulus N. Then the key E is the public exponent, D is the private key. Now let us try to encrypt. Let's take a small message m equal to 3. Let us try to encrypt this message m equal to 3. Okay, so m is 3. So encryption is nothing but raising m to the power e, exponent e. Okay, and then you have to take the modulus. So modulus n. So that is the cipher C. So let us see the value of C. So this is the encrypted plain text message. This is the encrypted message for the value m equal to 3. Now, is it possible to decrypt in plain Python? If you try to decrypt, typically what we will do, you take the ciphertext, raise it to the power D, right? That is the private key. If you try to do that, it will run forever because the value of D is so large, the exponentiation will take forever. So with the plain Python, you cannot do that. Let's try actually. So let's try. See, it will never come out. It will run forever. It will never come out. So most of the cryptographic libraries, what they will do is they use the efficient algorithm to calculate the exponentiation. They don't use the plain, like manually when you exponent, right? Let's say 2 power 3, 2 star 2 star 2. You do, right? They don't do that. Instead, they use a efficient algorithm. So for that, what I will do is the key that we created, right? It contains all the necessary objects. So if you don't know what are the objects it contains, you use the Python help command. It will tell you, for example, look at this. It has a decrypt function, it has an encrypt function, lot of other things, right? So let's use the inbuilt function for encryption and decryption. Okay, so k dot encrypt the message m, right? So m is nothing but 3. The second parameter I will not use. So this is the encrypted value. We already stored the ciphertext in the variable c, right? So let us look what we manually calculated. Look at this, both are same number, right? So instead of manually doing, we can actually use the inbuilt encrypt function. So let's use the inbuilt decrypt function. So my ciphertext is c. If it's properly decrypted, I should get the value back, right? My plain text is m equal to 3. So I should get the value 3. Let's see. So I got the value 3. Okay, so far we learned using RSA how to do the encryption and how to do the decryption. Let's move on to the next topic. Okay, next we will look at the multiplicative property of RSA. So what is that? So let's say you have a message M1, right? You first encrypt this M1 alone. You will get ciphertext C1. Then you take another message M2. You encrypt alone. You get ciphertext C2. Now multiply both the ciphertext C1, C2. Of course, if you multiply, it's going to become a large number. So usually whenever we do multiplication, we also take a mod n. This is going to be equal to, you directly multiply both the plain text M1 and M2. You multiply both the plain text. The resulting product, you do the encryption. And then as usual, you take mod n. So this relationship is called multiplicative property of RSA. Later we will use this property in our Bleichenbacher attack. So before we move further, let us first see using Python whether the property is really true. Okay, let's take two simple messages m1 equal to 2, m2 equal to 3. So let's encrypt these guys. K dot encrypt m1. As usual, the second parameter I am going to give none. Okay. C2 is nothing but k dot, sorry, k dot encrypt m2. Second parameter is none. Let's look at this value. C1. If you notice the C1, right, it's in a tuple. Okay. So we don't want a tuple, so we'll only take the first value of this tuple and store it in C1. So C1 equal to this. Similarly, the first value we will take and store it in C2. C2 is this. Okay. Now let's multiply these two values. Our left hand side is equal to C1 star C2. We will multiply and then whatever result we will do a mod n operation. So let us look at the left hand side value. This is the value we got. Okay. Now for the right hand side, what we will do is k dot encrypt m1 star m2. As usual, the second value is none. Whatever is the result is going to be a tuple. So I will take the first value from the tuple, modulus k dot n. So that is going to be my right hand side. So let us look at the right hand side value. Look at this. Both my left hand side value and the right hand side value are equal. That means the multiplicative property of RSA is true. Okay. Next, we are going to look at the PKCS padding format. When RSA security company created the RSA standard, they also created a set of public key cryptography standard. This standard was actually created by the RSA company, RSA Security Inc. Later, they provided this standard uh, for the RFC purpose. So they have large number of standards starting with the number one. This is standard number one. They also have standard 2, 3, 4, etc. So PKCS stands for Public Key Cryptography Standard. The one we are going to use is that deals with RSA is standard number one. It defines the RSA encryption, what kind of padding you should use, how you should go about encryption, all the fine details are defined in this standard. This standard has multiple versions. We are going to look at version 1.5, which is usually in SSL and TLS. Actually 1.5 is not very safe. There is another version available called 2.0, but unfortunately SSL TLS is stuck with version 1.5. This is also documented for public use in RFC 2313. Inside this standard, there is a section called padding format. That is, whenever you want to encrypt a plain text using RSA, you cannot directly encrypt the plain text. You must follow this particular padding format. So I have taken the paragraph from the RFC. It's called encryption block. The encryption block should always start with 00. It's a hexadecimal 00. The first byte is always 00. The length of the encryption block, that is this length, right? The length of this encryption block is equivalent to your size of the modulus. Let us say in our case, we use modulus equal to 2048 bit, right? So if you convert it to byte, it is nothing but 256 bytes, right? So this is nothing but 256 bytes. So this is your length of the encryption block. In our case, it's going to be 256 bytes. The first byte is always 00. The second byte is called block type. BT stands for block type. In this attack, we are only going to deal with the public key operation, that is encryption operation. So we will not worry about the signature. You can also use RSA for digital signature. We don't go into that. For this attack, we only need the encryption operation. So for public key operation, that is the encryption operation, the standard says use the value 02. So the first value is 00, the second value is going to be 02, all in hexadecimal. Okay. Then you use a set of padding string. So PS stands for padding string. It has to be at least minimum 8 bytes. You cannot use less than 8 bytes. It has to be at least minimum 8 bytes followed by a 00 as a separator. The padding string and plain text. So this is the padding string. This is the plain text. Both are separated by this 00 marker. Okay. Now you have your plain text. You arrange accordingly. Okay. You put enough number of padding bits so that your total size will become 256 bytes. So this is the recommended padding format in version 1.5. Now we will look at how this padding format is utilized in SSL TLS handshake. But before that, I want to show you something. Let me go back to the terminal and show you something. How does this padding format work using the openssl and RSA utility? Okay, let us play around a bit with the PKCS 1.5 padding format, for which I am going to use the openssl command. First, let's use the openssl command and generate a RSA key. So my output I am going to store in a file called key. The key size is going to be 2048 bits. So it generated the key. So if you have noticed, it used the exponential value as 65,535. Now let's open this file and see how the content looks like. My input file is key. I'm going to see it in a text format. So let me see. So this is my private key in the PEM format. We don't have to worry about this. So your private key is 2048 bit long. Your modulus, this is your modulus value, and then your e value is going to be your public key, right? Then your private exponent is your private key, the d value that I have discussed in the beginning. Then you have your p prime 1 p value, you have your q value prime 2 q value. You will also see some more stuff that we don't discuss now. That stuff is usually in Chinese remainder theorem for easy calculation of RSA stuff. So we don't need all those info. Okay. Next, what I'm going to do is I have a file here. I have stored some content in a file called pad. Basically, in this example, I am using the modulus n equal to 2048 bit. That means the encryption block that I should use in my padding must be 256 bytes. Okay. So I am using a echo command. Minus n means do not output a new line at the end of this command. Minus e means accept the backslash character escape sequence. So this is my input string, padded input string. I am going to encrypt a single letter. My letter is hexadecimal 61. So I am separating the padding and my plain text using a hexadecimal 00. So after the initial 00, I told you it should start with 00. For public key operation, the block type must be 02, right? That means it should always start with 0002. Thereafter, until you encounter the first 00, these are all padding bytes. Okay. In my case, the overall block is 256 bytes. So I have added 252 padding bytes because this will consume 1 byte. The 0002 consume 2 bytes. This fellow consume 2 byte, 4 byte. 256 minus 4, 252. So I have added 252 padding bytes here. Actually, you should use a random string as padding byte. Don't use the same character as padding byte. Okay. Okay. Now this is the hexadecimal 61. If you don't believe me, you can see the ASCII command. So the lowercase letter L, the hexadecimal value is 61, right? Okay. Then I will pass the plain text A to the open text. That means I manually constructed this padding format so that you will get an idea how it is used later in SSL TLS. Then I am using the openssl RSA utility dash encrypt. My input key is key. In key means my private key. Sorry. My key file is in key. This key file contains both the public key as well as the private key. Okay. So during the encryption, it will use the public key, and then during the decryption, first I encrypt. Again, I will pass it back to the decryption so that I know whether it's encrypted properly or not. Both the place I use the same key because the key contains both public key as well as the private key. Okay, now I am going to use this command. Okay, so let me type this command and cut and paste and execute this command. So I will cut and paste. I am going to execute this command. Okay, let me clear the screen. I should get a lowercase a as output if everything goes fine. Okay, I got a lowercase a. The percentage character you are seeing because I am not ending it with a new line. That's why my cell is prompting a percentage character. Okay, this is doing a okay. The reason I use the raw command is if you don't use the raw command, by default OpenSSL will try to do this formatting for you, padding for you. I don't want that to happen. I want to learn. So I manually do the padding and tell OpenSSL don't touch anything. Whatever string I give, just use the raw format and encrypt the string. That is the meaning of dash raw here. Okay. So we took a perfectly padded string to encrypt. Now let's play around with this padding to see how OpenSSL will produce error. Okay. Let me go back. First thing I will do is instead of the minimum 8 byte that is needed, I will purposely introduce a 00 here. That means my padding byte is now only 1 byte. Anything after the first 00 will be considered as plain text. So all this highlighted thing will be considered as plain text. Okay. Because I am only using one padding byte, OpenSSL will going to throw a error. Let's see what happens. See, it says PKCS decoding error. That means I cannot decode. Your padding check is failing. Something wrong with your padding. Please go and correct it. Okay. So now what I will do is, instead of here, I will continue f of here. First byte. So let me take 7 bytes. 1, 2, 3, 4, 5, 6, 7. Right. I need minimum 8 byte of padding, but purposely I will make this 1, 2, 3, 4, 5, 6, 7, 8. I will purposely make the 8th byte here as 0, 0. So it will still fail because there is not sufficient padding bytes, right? So let's see. So it is still failing. So it still says, hey, the padding check is failing. Looks like you are doing something wrong. So I will come here. This time I will use exactly 8 bytes. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to use 8 bytes. Okay. So minimum, I have met the minimum 8 bytes. So anything after the first 0, 0 will be considered as plain text. Okay. That means I am passing junk value as plain text. Of course, output you will see junk. So let's see what is the output. So this fellow successfully encrypted and the following openssl command successfully decrypted. You will see some junk because all the junk correspond to the f of character. You also see my plain text A, right? Here is my plain text A. So we learned that we need a minimum of 8 bytes for the padding string. It should start with 0002. After the padding string, you should pass a 00 as separator. Now we do one more thing. Instead of the required block size, because we are using modulus value as 2048 bit, we need exactly 256 bytes. Okay. Now what I will do is, I will purposely remove 1 byte and make the length as 255. I will remove purposely 1 byte. Now the length of this encryption block is 255 bytes. Let's see. So our guy is saying data too small for key size. That means you are not meeting the block size. The encryption block size must be equivalent to your modulus size. In our case, modulus is 2048 bits, that is 256 bytes. I purposely passed 255 bytes, that's why it's failing. So I will go back and correct my mistake. Okay. Let me go back and correct my mistake. I will introduce one more byte here. XFF. Now it should work. Okay, it is working now. Okay. So that's how the PKCS version 1.5 padding formatting is working. Next, we will look at the SSL TLS handshake during a RSA key exchange. When you use the RSA key exchange, let's say in the beginning you have a client and the server will use a RSA certificate for RSA key exchange. The client will send a client hello message, followed by the server will send a server hello message, followed by a server certificate, followed by the server hello done. Then the client will send what is called a client key exchange message. At this time, the client will generate a 46 byte random number. Let's say this is the 46 byte random number. Okay. Then in the client hello, typically it passes the TLS version number. Let's say you are using TLS version 1.2. The reason for for TLS 1.2, the hexadecimal code is 0303 is the version number. So it will take these 2 bytes and then it will prefix these 2 bytes at the beginning. So in our case, let's say it is 0303. So together these 2 byte and 46 byte, you will get total 48 bytes. The reason why it attaches this 2 byte is to prevent the downgrade attack. Okay, TLS downgrade attack. So you will get a 48 byte number, right? This 48 byte number is what we call as pre-master secret. This pre-master secret, the client will take this and pad according to PKCS version 1.5 padding format. And then it will encrypt this using the server RSA public key. So basically, the client key exchange message will contain this encrypted pre-master secret and it will send this to the server. The server will use his private key to decrypt this and get back the plain text. So from this, the server will use a pseudo random function and calculate a master secret. Again, it will use another pseudo random function and calculate the ultimate key material. So this is the final key you are using to encrypt the application data. That is the symmetric key that you are using. Okay. So you don't have to worry about all these things. We are only focusing here for pre-master secret. So in summary, if you want to decrypt a packet, you definitely need the pre-master secret. Okay. Okay, let us look at a sample RSA key exchange SSL capture file. Just for testing purpose, I use openssl S client and S server using my loopback interface. I captured this. So this is using a RSA key exchange. So if you look at the client hello packet, go to the handshake protocol. There is a initial TLS version and number, right? We are not going to use this. You have to go inside the client hello, handshake protocol client hello. Inside the client hello, you will see the actual TLS version number, that is 1.2, right? So 1.2 is nothing but 0303. This is the 2 byte we are using during the padding operation. I told you, right? Client will generate a 46 byte random number, prefix this 2 byte, that is the version number inside this client hello. Don't take the wrong one, don't take this one, okay? It is inside the client hello message. These are the 2 byte I am prefixing to generate my pre-master secret. And then if you look at the client key exchange, inside the client key exchange message, because I used the RSA certificate, my modulus is 2048 bit. That means my encryption block inside the PKCS padding is going to be 256 bytes. That's why it says 256. So it's already encrypted. There is no way you can decode this. Only the server is able to decode this, because to decode this you need the server RSA private key. Okay. Now let's come back to the command line. So here what I have did is, if you have noticed the application data, right, is already decrypted, right? Get slash http 1.0, it's already decrypted. The reason is I have already passed the private key to decode this thing. So if you go to the protocol preference, I have already passed the key. This is the private key that I am using. Okay. When you pass the key, what Wireshark will do is, you should also pass a SSL debug file. If you pass this SSL debug file, step by step how it decrypted, it will write down in the debug file. So there you can see it collected the encrypted pre-master secret and then it decrypted and then it will strip the actual 48 bytes of pre-master secret. So let's see. So I have my wireless debug file. Let me open this and see how it has done. So go down, go down, go down, slowly go down. At some point of time it will receive the client key exchange message, right? So yeah, it got the client key exchange message. So we are waiting for my client key exchange message. Where is this client key exchange message? Yeah, I got my client key exchange message. Then it retrieved the encrypted pre-master secret. This is the encrypted. So 256 bytes of encrypted pre-master secret it is storing in an array. Then it uses the private key file that we supplied and then decrypted. Okay, it just decrypted. It has not yet removed the PMS from the decrypted value. That's why it says unstrip. Unstrip means I just decrypted. I have not yet removed the PMS from this. So the decrypted file will the decrypted content is also 256 byte. Because this fellow is starting with the 00, Wireshark typically will not print 00. That's why it's only printing the remaining 256 bytes. So if you come down right, sorry, if you come down right, you can see the final thing is empty, right? The final thing is empty because it is not printing the initial 00. That's why it's only storing the next 255 bytes. Okay. So this is our decrypted pre-master secret. But I told you it is in the PKCS padding format. That means it is starting with 0002. I told PKCS 1.5 padding format for public key operation always start with 0002. Then until you hit 100 separator, all bytes are padding bytes. So you wait for a 00. This is the first 00. So that means all the highlighted contents are nothing but padding bytes. Okay. This is the separator. This 00 is the separator. The first 00 is the separator. Then you have your remaining 48 bytes. This is our pre-master secret. If you look at this 48 byte, the first 2 bytes start with the TLS version number that we saw in the client hello, right? So if you look at the client hello, go inside client hello, TLS version number is 0303, right? So this is what you are seeing here, 0303, first 2 bytes, then the remaining 46 bytes generated by the client. So together this 48 bytes is called pre-master secret. You can see that in the next step. So Wireshark basically will retrieve this 48 bytes. So you can see it is starting with 0303, which is nothing but the TLS version number inside the client hello packet. So this is your pre-master secret. So that's how Wireshark is decrypting and retrieving the pre-master secret 48 bytes. Okay. Now we will look at what is an oracle. In cryptography, an oracle is nothing but a black box. So let's say you have a black box here. Okay. It has a well-defined input and output. For example, let's say this black box, whenever you provide a number, it will tell whether the number you gave is a odd number or even number. So you know what is the input that you need to give, and you can also collect the output, but you have no idea how this black box is calculating and deciding whether the number you gave is odd or even. That means the internal logic of the black box you have absolutely no idea. The only access you have is input and the corresponding output. So whenever you give a number, for example, if you give, it will say you have given your odd number. If you give 4, it will say you have given a even number. So you only have access to the input and you have access to the output. That is what we mean by oracle in cryptography. It's a black box with well-defined input and output. You have no idea of how this black box works. Okay. There are various kinds of oracle that cryptanalysis are using to break the thing. Bleichenbacher attack uses what is called a PKCS padding oracle. So let's take an example of SSL. In SSL, when you use a RSA for key exchange, the client will typically send a client key exchange message to the server during the handshake. This client key exchange message will contain the encrypted pre-master secret. The server will collect this encrypted pre-master secret and it will try to decrypt this. So after decryption, he will get the so-called padding block, right? In the padding block, what I mentioned, the encryption blocks will contain, it will start with value 0002. These are all hexadecimal value, followed by some padding bytes, padding string, followed by a marker 00, followed by your PMS value, right? So this is what we mean by encryption block. But after decryption, the server is still not sure whether it's properly formatted or not. So what it will do is it will send this entire decrypted text. This is the decrypted text. It will send this entire decrypted text to the padding oracle. This padding oracle will check whether it is compliant to the PKCS formatting or not. If it is compliant, then it will return a true value. Otherwise, it will return a false value. So if it is compliant, then the server will go ahead and try to extract the PMS and proceed further. If it is a false, then the server will straight away send a error message, that is a padding error. So this is roughly how it works in SSL TLS. So the job of a padding oracle here is, after decryption of the message, the resulting text, is it compliant to the PKCS padding format or not? If it is compliant, it will send a true value. If it is not compliant, it will send a false value. Finally, let us look at the Bleichenbacher attack on RSA. In 1998, Daniel Bleichenbacher published a paper titled Chosen Ciphertext Attack against protocol based on the RSA encryption standard PKCS1. So in this attack, basically he will make use of a PKCS padding oracle and the multiplicative property of RSA. So we already discussed the padding oracle as well as the multiplicative property of RSA, right? So before we move further, let us first see what is a chosen ciphertext attack. In cryptography, it is called CCA. In a conventional CCA, the aim is to recover the key that is used for encryption. The assumption is the attacker has access to a decryption oracle. Let's call it a decryption oracle. So what is a decryption oracle? Whenever you provide a ciphertext C, the decryption oracle will provide corresponding plaintext P. That means the attacker can initially send C1 and he can get the corresponding P1. He will continue this step n number of times. Let's say he sends Cn and he will get Pn. By using this knowledge of the ciphertext and the corresponding plaintext, eventually he will be able to recover the key K. So this is how the chosen ciphertext attack is working. However, in the Bleichenbacher attack, it uses a different version of CCA. That is, it does not have access to a decryption oracle. Instead, it only have access to a padding oracle. That means the aim here is not to recover the key. Instead, only to decrypt the initial ciphertext. For example, in case of SSL, the initial ciphertext is going to be the encrypted pre-master secret. So your ultimate aim is to decrypt this and figure out the pre-master secret. So this is very important. You need to remember, because when you read different cryptography books, they always say chosen ciphertext attack means to recover the key. The attacker has access to a decryption oracle. Whereas in Bleichenbacher attack, it uses a different version of chosen ciphertext attack. The attacker does not have access to a decryption oracle. Instead, he only have access to a padding oracle. Okay, so you keep this in mind. So here how the attack work is, initially you have the encrypted pre-master secret, right? Let us call this C. This is your initial ciphertext. So you multiply this with something. We will discuss all these things a bit later, and create a new ciphertext C1. You send the ciphertext C1 to the padding oracle. The padding oracle will say whether it is PKCS confirmed or not. If it says if it is not confirmed, you increment the value. Whatever value you are using here, you use a small integer, you increment the value until the padding oracle says the resulting ciphertext is valid. It's valid and it's able to decrypt, and the padding conformance is also okay. So you use this knowledge and again repeat this step with a every time with a different ciphertext, Cn something, right? So with all this information, eventually you should be able to decrypt the original ciphertext and you can recover the PMS value. Don't worry if you still don't understand. In the next step, we will see how it does. So in summary, the attack used in Bleichenbacher is called adaptive chosen ciphertext attack, because after every step, when the padding oracle is succeeding, you use this knowledge to carefully create another ciphertext, and then in the next step you pass this ciphertext. So every step is based on the outcome of the previous step. That's why we call it adaptive chosen ciphertext attack. Let us look at the core concept of the attack. So in the beginning, from the client key exchange message, you have the encrypted pre-master secret. Let us call this C. This is the one you are planning to decrypt ultimately. In the RSA multiplicative property, we learned that if you have message M1, if you encrypt this message, and you have message M2, if you encrypt this message under mod n, this is nothing but equivalent to multiplying both the message and then encrypting this message under mod n, right? Now let us say the first encrypted cipher is nothing but your C here. You take a small integer s and raise it to the power e. Okay, in RSA, if you take a message and raise it to the power e under mod n, that is nothing but equivalent to encryption. Okay, That means if you write this integer to the power e, it is equivalent to encrypting the value s. So that will become your second encrypted text, this so-called s power e. Okay. Now if you multiply these two, the result is going to be the multiplication of the corresponding plain text. Okay. So your corresponding plain text is pre-master secret and the value yes. For simplicity, let me call the PMS as simply M. That means multiplication of C and S power E is nothing but you take the corresponding plain text and then encrypt it. If the padding oracle, let's say if the padding oracle say this is a valid padding, after decrypting this message, if it is a valid padding, that means you roughly know in which interval this message is occurring. So the padding oracle is telling true. Okay, if the padding oracle say true, that means it's a valid. The MS is a valid and it is conforming to the padding. So we will know the initial value of this MS. Where what is the initial value of this MS? Although I don't know the value of M, I do know the value of S, but I can roughly guess what is the initial value of this MS. The reason is, let's say I told you in the padding format, the encryption block is nothing but it is starting with hexadecimal 0002, right? That means you already know the first 2 bytes. So in our example, let's say this encryption block, I am using a modulus value of 2048 bytes. That means the length of this modulus is nothing but 256 bytes. Okay. So my encryption block length here is going to be 200 256 bytes. So out of this, I already know the first 2 bytes. After that, I know that there is a padding string followed by a marker 00 followed by this PMS value. So the only unknown value is remaining 254 bytes. So if I write it in hexadecimal, so this is your interval. So this is your initial interval. It can be greater than or equivalent to A and less than or equivalent to B. Okay. So the A value here nothing but it is starting with hexadecimal 0002 followed by something which you don't know. So let's say the beginning value is 00 dot 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 all 0, that is you call it as A. So the ending value is going to be 0002 all ff dot 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 ff. So this is the ending value. So let us call this ending value as B. That means your message is sitting somewhere between this value, right? That is your so-called MS is greater than or equal to A and less than or equal to B. So I have a guess. I know this interval. So to make things easier, let me give you a similar example so that you can understand it much better. Let's say I am the attacker, okay? I am the attacker here. Okay? You are the guy. I am asking you to guess a number between 1 and 1000. My job is to figure out what is the number that you have guessed, okay? For that I am going to play some trick on you for which you need to answer. So let's say for example the number you guess is 12, okay? I am going to figure out this by asking certain questions to you. The first question I am asking you is, hey guy, can you tell me whether the number you have is divisible by 2? Is it divisible by 2? You are checking. Yes, it's divisible by 2. Then you are telling, yes, it is divisible by 2. I see. That means I don't have to check all the 1000 numbers. Instead, I can only look at the even numbers. Okay. So instead of checking the 1000 numbers, now I have reduced my search interval to just 500 numbers. Okay. Now I am asking you, hey guy, the number that you have, is it divisible by 3? You are telling, is it divisible by 3? Yes, it's divisible by 3. Okay, it's divisible by 3. I see. Now I reduce the interval further. So let's see a quick demo. I just wrote a very crude Python script for a demo. So let's see a demo. So initially I am asking, is it divisible by 2? You say yes. That means I don't have to check 1000 numbers. Instead, I will only look at all the even numbers. So this is the set of even numbers. So total number is 500. Okay. Then I am asking, Is it divisible by 3? Because you have guessed 12, you are saying yes, it's divisible by 3. Okay. Now I don't have even to change 500 number. Instead, I reduce my interval. So this is my reduced interval now. So I only have to look for 166 entries in this number. Okay. Now I am again asking you, is it divisible by 4? You are checking, yes, my number is 12, yes, it's divisible by 4. Then you are telling it's divisible by 4. Look at this. So in just 4 steps, instead of looking at 1000 number, we have reduced our search interval to just 83. In Bleichenbacher attack, we use a similar step to reduce the number of intervals. At every step, when the padding oracle gives a positive answer, you will reduce the number of intervals. So that's how the Bleichenbach attack is working. Okay. So at every step, you try different value of S and create a new MS value and then send it to the guide. Eventually, by reducing the interval, finally you will end up with a single value. So both the starting number and the ending number is going to be the same. So that in that case, this A is nothing but your MS. Okay. You know the value of M, you calculate the modular inverse for it, and then you multiply both MS and the inverse value. This will get cancelled. You will get back the original message M. So the M is nothing but the pre-master secret. Okay.
Okay, it's demo time again. Let's see a demo of this Bleichenbacher attack. For the demo, what I am going to do is, instead of performing the attack over a real TLS connection on a server, to save some time, what I will do is, I will take a SSL encrypted packet capture, which is using a RSA key exchange. Okay, from the packet capture, I will take the encrypted pre-master secret inside the client key exchange. Okay, so let's see. For example, I'm going to use this packet capture for my demo. As you can see, we cannot read the application data. It's completely encrypted, right? We cannot see what the application data is. Our aim is to decrypt this packet capture using the Bleichenbacher attack. So for that, what I will do is, I will go to the client key exchange. I know that this packet capture is using RSA key exchange. If you don't believe me, you can check from the server hello. In the server hello, the cipher suite says it is using the RSA key exchange. Okay. Now I will go to client key exchange. Client key exchange is the place where the client generates a random number and encrypt it and send the encrypted pre-master secret inside the client key exchange. This is the client key exchange. So inside you have your encrypted pre-master secret. So I will just right click this. I will copy this value as a hexadecimal stream, as a set of hexadecimal stream. I will come back to my Python source code. So this is my Python source code. So inside my Python source code, I copy this encrypted pre-master secret. So this is going to act my initial ciphertext C. My ultimate aim is to decrypt this value using this attack. So let us perform this attack. So performing this attack, what I am going to do is, I will use the Python 3 command. I am using a Ubuntu Linux here. This is my source code. Since the attack is going to take some time, I will redirect the output to a text file so that once the attack is performed, I can go back to this text file and see the intermediate steps of the attack. So let's start this attack. So I'm going to press enter. So the attack is going on. It is going to take some time. So depending on the size of your key and your real network condition, here I am not using a real network, but if you perform over a real network, right, the attack can take anywhere from say 4 hours all the way to 8 hours, and it may need a large number of calls to the oracle. For example, in simplest case, we can even able to break it with, let's say, 30 or 35,000 calls to the oracle. Or in some, if your key is very strong, or in a complicated case, it can even take 100,000 or 120,000 calls to the oracle. So it all depends on the key. Also, it all depends on how efficient your attack algorithm code is. So the code that I am using is not a very efficient one, so it is going to take some time. So let me wait for the output to get complete.
Okay, my program has completed. So let us look at the output that it has generated. So if you look at the output, I told you at every step when we send a ciphertext to the oracle, and if the oracle succeeds, that it will generate a new interval in which you can find the message, right? I told you depending on your key, it will end up in a single interval or multiple intervals. For example, in our case, this is the first a value. Look at the size of the integer, so big, right? So your message in RSA is nothing but a long integer. So this is my initial a value, comma my initial b value. That is, your message can be anywhere inside these two intervals, greater than or equal to a, less than or equal to b. In this case, it so happened it found two different intervals. So there is c comma d. There is one more interval c comma d. So your message is either in a comma b or in c comma d. So at every step it keeps on narrowing down this interval. So if you look at the end, right, eventually it will end up with a single interval where both the numbers are same. Look at the last four digits, 6022, 6022. Basically your a value, this is your a value, the a value, your lower bound, and your b value upper bound, both are same. That means we will narrow down to a single point and we found the ms value. You know your s value, so you find the s inverse and multiply to this number, you will get your m. So your m is nothing but it has found the pre-master secret. So this is your m value, the initial pre-master secret that the client sent. So if you notice this, it has taken us 91,971 calls to the oracle. I mentioned to you, right, in a real network when you perform, depending on the strength of the key and the network condition, it can take even more. Like for some of the key that I tested, it took like 115,000 also. So if you look at the pre-master secret, total it is 48 bytes. It is written in hexadecimal, 48 bytes. The first two bytes are 0303, meaning it represents the TLS version number which it found in the client hello. I told you, right, when I described the padding format, I told you the first two bytes of pre-master secret is nothing but the TLS version number in the client hello. The remaining byte, 46 byte, is a random number generated by the client. So together is 48 byte. So let us use this number and try to decrypt our packet capture. So initially the packet capture is totally encrypted. We cannot see what is the plain text, right? So our aim is to use the PMS that we found using the attack and then decrypt this packet capture in the Wireshark. So let me copy this. Okay, let me copy this PMS value. So if you remember your Wireshark, right? So in the Wireshark, if you want to decrypt, you have to create a PMS file. So let's call it PMS. So the Wireshark expects a format starting with the keyword RSA followed by first 8 bytes of the encrypted pre-master secret. So let me go to client exchange. Let me copy the encrypted pre-master secret. I don't need the all bytes. I only need the first 8 bytes in order to decrypt. So let's copy it as a hexadecimal stream. So I am going to copy it here. Like I mentioned, I don't need all the bytes. I only need the first 8 bytes. So 1, 2, 3, 4, 5, 6, 7, 8. The remaining I don't need. Okay. Now I will take the PMS that we found using the attack. I will cut and paste this PMS. So this is the PMS I want to cut and paste. So my PMS file is ready. I will use this PMS file in my Wireshark. So let's go to the Wireshark. You right click this, go to protocol preference, go to the pre-master secret log file name. You basically have to tell where this log file is. So I stored it as a PMS. So after you pass this, if it is fine, you should be able to decrypt it. Okay. Success. We are able to decrypt. Look at this. Instead of finish message, you are able to see the alert message. You are able to see the encrypted alert, which is a finish message, right? You can even see your application data. So if you come down, let us expand this a bit. Go to the decrypted SSL. You can see it is decrypted. Get command get slash http 1.0. So finally we decrypted a encrypted SSL capture using the Bleichenbacher attack. So how do we mitigate from Bleichenbacher attack? If you are using a non-SSL TLS protocol, the general mitigation is if you encounter any processing error, do not inform this to the client. Just give a generic error message to the client. Don't give any clue what is happening on your side. When we come back to SSL TLS, the RFC for TLS version 1.2 clearly has a section on this, how to prevent from Bleichenbacher attack. So this RFC section says, if you encounter any processing failure during the encrypted PMS processing, do not inform this failure to the client. Instead, you just go ahead with your own PMS, generate your own PMS on the server side and use it. Of course, because now the PMS is different on client and server side, eventually during the finish message step it's going to fail, but that is okay. The idea is don't give any clue to the client. If you encounter any error, don't give any clue. Any clue you give, he will make use of this clue and perform a chosen ciphertext attack. Actually, there are a lot of variation of this Bleichenberg. I always have a tough time pronouncing this name. Bleichenbacher attack. Several variation exists. Even some of the advanced variation exist. In some variation, we can even perform a signature forgery attack. So we don't have time to go into all those details. So my idea is just to tell you how the basic attack working. That's it. Okay. In summary, the Bleichenbacher attack uses a adaptive chosen ciphertext attack in which it makes use of a PKCS padding oracle. Using this oracle, it's able to eventually decrypt the initial ciphertext. So the aim here is not to recover the key, instead decrypt the ciphertext. That is our aim in Bleichenbacher attack. Okay, thanks for joining today's lecture. If you have any questions in my presentation as well as in demo, you can send me an email. I will try to answer you. Thanks a lot for joining this presentation.